Welcome back to the second module of the third week. We continue our exploration of greedy algorithms, and this time, as I had mentioned, we will be talking about a problem called Islands War. This was the fourth problem of a ABC contest on AtCoder. It was contest number 103. You can find a link to the problem statement in the description of this video. And this one turns out to be a problem with a really fun story about warring islands, as you can guess from the name of the problem. So there's going to be a lot of conflict and drama, and your task will be to figure out how you can resolve all of these conflicts with minimum damage. So we're going to have a lot of fun. Let's get started. So the first thing that we are given is that we have n islands lining up from west to east, connected by n-1 bridges. And these bridges are not completely arbitrary. The ith bridge is given to connect the ith island from the west with the i+1th island from the west. So it's a really clean visual. Here is an example with 10 islands. And the bridges, there are 9 bridges which just connect them from left to right. So west to east has been sort of modeled as left to right on your screen. So the westmost island is the first island here, and so on. Now, the real story begins when we are told that some disputes have broken out between some islands, and we want to make traveling between those islands using these bridges impossible, right? And of course, how do we do this? We must have something to work with to be able to meet this goal. And the thing that we are allowed to do is we can remove some of these bridges, okay? But as you can imagine, removing bridges is a fairly destructive thing to do. So what we are also asked to do is to minimize the number of bridges that need to be removed. So you want to pacify everybody involved in a dispute. So in the language of the problem statement, these disputes are called requests. So we are given m requests. Each request is a pair AI-BI, indicating which pair of islands are involved in the corresponding dispute. And what you want to do, of course, is you want to remove bridges in such a way that every request is satisfied. So that's the entire problem statement, that's the goal. And what we are going to do is just try and think about this first with the help of a few scenarios. And in fact, before we get to actually thinking about specific examples, let's go through this one right here. So as you probably have noticed already, we have 5 requests here. And a useful way to visualize these requests, because we want to be thinking about which bridges to remove to satisfy all of these requests, we're going to visualize these requests as lines that have their endpoints at the 2 islands that are involved in the request, right? So let's just draw these out here, and now maybe you can just try to figure out what is the optimal solution for this example, just to get a feel for the question, to make sure that we are on the same page with respect to the task at hand, right? So feel free to pause here, because I'm just going to give it away after I finish this sentence. So for this example, you may have noticed that it's impossible to meet all requests by destroying just one bridge, because for instance, we have a pair of disjoint requests. So we have 2 requests that don't have any bridge that is common to them, right? So there is no single bridge that will handle both of these requests. So you need at least 2. And the interesting thing is that you can do it with just 2 bridges. So you could, for example, remove these 2 bridges here and you would be done. So how do we go about thinking about this problem in a greedy fashion? What is a natural greedy strategy? Remember that we have to meet all requests, and we have to minimize the number of bridges that we use to actually satisfy these requests. So what sort of bridges should we prioritize? What sort of bridges are likely to appear in an optimal solution? So a natural thing to do is to probably just go over every bridge and count how many requests are such that they would be satisfied if we were to remove that bridge. So you could call this the power of a bridge or something like that. You could use whatever term seems natural to you. I'm just going to go with power. So let's say that the power of a bridge is just the number of requests which would be handled if we were to hypothetically destroy that bridge. Now it seems to make sense to target the bridges that have the highest power, because the more powerful a bridge, in some sense, the more requests you handle in one shot. So this motivates our first greedy approach to this problem. What we could do is compute the power of every bridge, sort the bridges by their powers, and then pick the most powerful bridges first. In particular, to begin with, we include the most powerful bridge in our solution, breaking ties arbitrarily, and then we delete all of those requests that got handled as a result of deleting this bridge. And then we keep repeating this as long as we have at least one request left. Remember that you may have to recompute the powers of the bridges, because after you delete some requests, some bridges may become less powerful than they were before. So you could do all of this, and what you would have as a result is a perfectly valid approach, but this is a good time to pause and think about whether it actually works. It will certainly produce a subset of bridges whose removal will handle all the requests just by definition, but the real question is whether this is the best that we can do. In other words, are we really getting to the minimum number of bridges that we need to destroy to handle all requests? So this is a great time to pause the video and actually think about this, play with some examples and see if you can come up with either an argument for correctness, or if you can come up with a counter example showing that this may not actually be the best possible strategy. So please go ahead and take that pause and come back to this video once you are ready. Okay, so hopefully you've had a chance to think about this, and it turns out that while extremely tempting, this strategy does not in fact work. So we're going to show you an example where the strategy of choosing the most powerful bridges can actually lead you to a solution that is not the optimal solution. So here we have a collection of 4 disjoint requests, which tells you straight away that the optimal answer has to be at least 4. And then we have a bunch of other requests which are going to play out over the next couple of seconds. Now let's try and think about what the greedy strategy would do here. So you can check that to begin with, there are 3 bridges that have a power of 4, and 4-5 is one among these most powerful bridges. So the greedy algorithm could start by picking 4-5 followed by 8-9, which is one of the most powerful bridges that are left in the second iteration. However, after deleting 4-5 and 8-9, you're still left with 3 disjoint requests, which means that the greedy algorithm will have to output a solution involving 5 bridges. However, notice that 4 bridges are actually enough for this instance. Remember earlier we said that we need at least 4, but it turns out that 4 bridges are even enough. Now you might be thinking that was pretty close. It was off by just 1. So do I really need to worry about this? So let me remind you once again that in contest programming, you have to get it exactly right. There is no partial credit for coming close to the right answer. Well, sometimes there are problem statements which will allow for solutions that are close to the optimal, but these are rare and certainly out of the scope of this course. So always work with the mindset of shooting for the exact optimum solution. Besides, although this particular example was off by 1, you can probably think about coming up with ways of modifying this example so that you can really amplify the gap between the output of a greedy algorithm that follows the strategy of destroying the most powerful bridges first and the true optimal solution. So I'll leave that to you as food for thought, while we should probably move on and get back to the drawing board and think about other alternate strategies. So to get a feel for what's going on, let's actually begin by looking at 2 really simple scenarios. These are probably the simplest scenarios that we can come up with, but they will still give us some intuition for what is going on. So first, let's think about what if all the requests were disjoint. Well, in this case, you know that there is no bridge that can handle more than one request. So you know that the optimal solution must involve at least as many bridges as there are requests. So opt is actually equal to M in this case. And in terms of actually coming up with a solution, if you had to, you could simply pick one bridge per request, and it could really be any bridge that kills that request. It wouldn't matter. On the other end of the spectrum, what if every request went over some common bridge? In other words, what if there was one bridge that was involved in every single request? So here is one example where this plays out, and you can probably, as we go along, identify the bridge that is common to each request. It's the one that's right in the middle. Now, when you have a situation like this, what should the optimum solution be? You can probably guess that the optimum solution is just that one bridge that every request is involved in. Now, a typical instance is going to be some combination of these two very extreme scenarios. So let's think about a more generic situation. Often it helps to think about what an optimal solution looks like, especially at the extremes. If there's some notion of beginning or end in a problem, it's worth thinking about what's going on the edge. So let's do that here. Let's think about a situation which has no special structure, but imagine that somebody has given you an optimal solution to look at. And one question that I would like you to think about now is, where is the leftmost bridge on this optimal solution? Where does it lie? Which request is driving the choice of the leftmost bridge? Please take a pause here and think about this, because this is going to lead us to the main insight for the final solution. So I hope you had a chance to think about that. We are going to work through this with an example. So let's draw up some requests right here. And as we said earlier, you really want to be thinking about which is that critical request that drives the choice of the leftmost bridge. There are some natural candidates. Is it the one that finishes first? Is it the one that starts first? Is it the one that finishes last? The one that starts the last? Well, if you think about it, you'll realize that it's probably the request that finishes first, because if you chose a bridge that came after this request finished, then you're in deep trouble. So we know that we have to at least pick the bridge 3-4 or one of the ones before it to make sure that the first request is satisfied. So in this example, we know that we have to pick at least one of these three bridges, 1, 2, 2, 3 and 3, 4, to satisfy the first request. Now the thing to think about here is, between these three bridges, is there a natural greedy choice to be made? Is there a bridge that seems to be at least as powerful as the other ones, so that we can sort of pick it at this stage without having to worry about exploring all the choices that we have? Well, a natural thing to target is the last bridge, which is the bridge 3-4 in this case, because notice that every request that can be handled by 1, 2 or 2, 3 can also be handled by 3, 4. If this was not the case, then we have a request that is being handled by the previous bridges but is not being handled by 3, 4, and that would contradict our choice of the bridge that finishes first. In case that was not completely clear, please take a moment to work through it. It's a simple argument, but it lies at the crux of why the strategy that we are going to propose is in fact correct. So the idea here is to simply prioritize the bridge that is on the brink of the request that finishes first, because again, the overall intuition is that we know that we do have to pick either this bridge or one of the ones that come before it, and it seems like this bridge is at least as powerful as the ones that come before it, so we might as well just pick this one. Let's convert this idea into an algorithm. The natural thing to do here is to sort the requests by their right endpoints, which is to say that the requests that finish the earliest will come first in the sorted order. And just to be sure, let's look at this sorted order for one of the examples that we saw just a little bit earlier. And now from here, what does the algorithm do? Well, it's going to look at the first request and pick the last bridge on it, and then eliminate all the requests that are handled by this bridge. And then we simply continue. For as long as we have a request left, we are going to be picking the last bridge on the first request. And notice that the sorted order of the requests remains unchanged even as bridges get deleted. So we just have to make sure that we track which requests are being handled by the bridges that we are including in our solution. So let's just play this out on a couple of examples to get a feel for what's going on. But at this stage of our discussion, you are actually exposed to the entire algorithm that finds a solution, and hopefully you have some intuition for why it works. We're going to have more to say about that and the running time in just a minute, but if you can't wait to implement this yourself, this would be a good time to take a pause and do it. In the meantime, let's play out the algorithm once again on one of the examples that actually appeared in the problem statement. And speaking of the problem statement, let me also remind you about the constraints that we are given on the inputs. So notice that the number of islands and the number of requests can be as large as 10 to the 5, which means that an algorithm that's either quadratic in n or m would not be feasible. In fact, even a solution that has a worst case complexity of n times m might get you into trouble. So let's analyze the running time of the approach that we have just proposed. Recall that in the first step, we sort the requests according to their right endpoints. So that's just a standard sorting procedure, and it'll take you time m log m, which is still pretty safe within the given limits. So the second phase is where we actually build up the solution. The way we did this was by performing one pass over the sorted list of requests, and every time we encountered a request, we would include the last bridge on that request in our solution, and we would also eliminate all the other requests that were handled by this bridge. But if you implement it exactly according to this description, then you have to be a little bit careful, because you might end up getting an order m squared kind of a running time, because every time you include a bridge, you do one more pass over the list of requests to identify those that need to be eliminated. So I'll leave it to you to think a little bit about how you can implement this in a slightly different way to ensure that all your work is being done in just this one pass over the requests. So one hint is that instead of actually explicitly eliminating requests as you go along, can you simply track the last bridge that you have included in your solution, and for every request that you're going over, simply check as you go along if it was handled by that last bridge or not, and think about why this approach would also work. So that is all that I'll have to say about the implementation for now, and I'd like to go back a little bit to our discussion about the correctness of this algorithm. So one of the really neat things about this algorithm is that the solution that it produces itself carries a proof of correctness. So if you think about the bridges that we chose finally, each of them corresponds very naturally to a request. So that is that request which triggered the choice of this bridge in the solution. Now, if you think about it, you will realize that all of these requests are in fact disjoint, because if they were not disjoint, then at least one of the overlapping requests would have been eliminated in a previous iteration. So you get a really simple contradiction. Now you have a collection of disjoint requests that is exactly the same size as the solution, which means that our solution has to be optimal. Going back to one of the first observations that we made, it was this really simple idea that you need at least as many bridges as there are disjoint requests in your instance. What this algorithm is telling you right now is that that's actually enough. You don't need any more. So it's this really nice duality telling you that, well, the largest number of mutually disjoint requests actually determines the number of bridges that you need to destroy. And that concludes our discussion about the algorithm and its correctness. Alright, so with that, let's move on to the implementation. So this is your regular spoiler alert at this stage of the discussion. If you want to try this yourself, of course, you should probably come back after you've given it a shot. But in the meantime, let's get started here. So let's recall that the first line of the input is just the number of islands and the number of requests given as two space separated integers. So let's just read those in. And the next m lines give you the m requests. So let's declare a list of requests and let's read these in. So I'm going to store each request as a tuple. You could also store it as a list, doesn't really make a difference. So let's say this is the current request which we are going to append to the list of requests. Now the first thing that we have to do is to sort this list of requests according to the right endpoint. So what we are going to do is use the built-in sort function on the list of requests, but we also have to tell the sort function to sort according to the second coordinate. And there are many ways that we can do this, but for brevity I'll just use a lambda function here. If you're not familiar with this sort of notation, you can look it up, but intuitively you can imagine that all that this is doing is it's instructing the sort function to sort according to the second coordinate of the tuples. Okay, so now that the requests are sorted the way we want them, let's actually get to the bit where we build up the solution. So let's declare an answer variable which we initialize to 0, and we'll start looking at these requests and figure out if a request really demands that a bridge needs to be added to the solution. So let's start by going over the requests one by one. And what do we need to know about this current request? What we need to know is it being handled already by the solution that we have built up so far or not? If it isn't, then we need to add the last bridge on this request to our solution. But if it is, then there's nothing to be done and we can move on. So how do we check this? How do we check if the current request is being handled by the solution that we have built up so far? Well, notice that if it is being handled by the solution, then certainly the last bridge in our solution covers this request, right? Because if the last bridge doesn't cover this request, then none of the previous bridges would either, right? And if it covers the request, then of course we are done. So it's enough to keep track of the last bridge in the solution that we have built up so far. So in some sense, what we are going to have is something like this. If the last bridge is at least request of 0. What does this mean? Look at where the request starts, right? And make sure that the last bridge is after the starting of this request. If this is the case, then the last bridge covers this request, yeah? And if this is the situation, then we can just keep going. But if it's not, then notice that we do need to add a bridge to our solution to handle this particular request. And what is the bridge that we are going to add to the solution? As we have discussed when we were going over the greedy approach, we said that it's enough to pick the last bridge that covers this request. So that's given by request of 1. So what we want to do is we want to add this bridge to our solution. So when I'm talking about request of 1, it's really the bridge that connects the island's request of 1 minus 1 with request of 1. So that's the bridge that I want to add to my solution. So remember that we're really just tracking the number of bridges in our solution, and as we go through this one pass over the requests, what I need to remember is what was the last bridge, or in other words, what was the rightmost bridge in my solution. So at this point, what you want to update is just the value of last bridge to reflect that the last bridge is now this one. It's the bridge that ends at request of 1. So by the way, I'm just thinking of representing the bridges by their right endpoints here. You could also You could also represent a bridge by its left endpoint, but then you would have to adapt the if condition in the previous block. The other thing, of course, that we have to update is the answer variable. We need to increment that by 1, and we need to print this answer. Of course, one thing that we haven't done is initialization. So what happens to the first request when you start this for loop? You're going to run into a problem when you try to execute this if statement, because there is no last bridge, right? We haven't even started building our solution so far. So to make sure that the last bridge of the first request is actually chosen in the solution, I'm going to initialize last bridge as -1, because that way, even if the request started at island number 1, it's still not going to be covered by this last bridge. Of course, notice that this is an artificial last bridge. It doesn't really exist. It's just so that the code that we have written picks up the last bridge of the first request to begin with, and then it does its thing after that. You could, of course, also initialize this as requests of 1 of 0, and then you could start your for loop from the second request onwards. So that's just going to be a matter of preference, but I believe this should work. I think we've gotten all of the moving parts right here, so I'm going to try and run this, and notice that the output here turns out to be 2. I think this was one of the examples, or at least close to one of the examples that we have discussed. We see that the expected output is also 2, and in general, as a matter of practice, you just want to make sure that your output tallies exactly with what is expected. We could run this on one of the other examples as well, and of course, as usual, you probably also want to run this on examples that you come up with, just to have an extra level of sanity check. But let's try running this on the last sample output, where the expected answer is 4, and this is also an example that we have actually seen. So let's go back and run our program, and we'll see that the output actually matches and everything seems fine. So on the samples, we're doing okay. And of course, I think we should have some confidence from the fact that we have discussed our approach by now in quite some detail. So at this point, I'd encourage you to actually check this code or a version of it that you might have put together on the full set of test cases, and let us know how it went. As usual, if you're stuck anywhere or if you're running into trouble with the logistics of submitting your solution, please give us a heads up on either the Discord channel or drop a message in the Google forums for this course, and one of us will be sure to get back to you. All the best, and we'll see you in the next problem. Bye for now.